Now that we know what the cryptographic hash function is, it is time to discuss how to construct them. This is very important because we use cryptographic hash functions in many different areas of cryptography. For this reason, we call it Swiss Army knife of cryptography. These areas include digital signatures, message authentication codes, pseudo-random number generators, key derivation functions, and so on and so forth. So let's discuss how to construct them. First thing you can do is, instead of trying to construct something new, we can use our other algorithms and convert them into a hash function. For instance, we can construct a hash function from a block cipher. So it is possible to construct a hash function from a block cipher where we replace the compression function with the block cipher encryption algorithm. So if you already deployed the block cipher, we might consider building a hash function from it, because we can make security claims about the hash function using the analysis of the block cipher. We can save space and implementation effort by reusing some of the components of the block cipher. So, however, hash functions constructed from block ciphers are generally slower than a hash function with a dedicated design. So this is important because dedicated designs like MD4, MD5, SHA-1, SHA-2, SHA-3, which we are going to see in the future, are somewhat faster than most of the block ciphers because they are designed to be a hash function, not a block cipher. But you can just simply use a block cipher and convert it to a hash function, and because with this you can get these two benefits. First of them is the security claims, and the second is to save space and implementation effort. And if you are using it on a hardware, just by using the same block cipher, you can obtain both encryption and a hash function. So how does it work? A compression function has two inputs, the chaining variable h and the message m, where compress function takes these values and compresses them. So this is the idea, because we already mentioned that a hash function has an input of variable size, but the output has a fixed size. So for this reason, you kind of need a compression function. A block cipher has two inputs, key and the plain text, and outputs the ciphertext. So if you try to form compression function like this, hi minus 1 mi equals to the encryption of the plain text with the key XOR C, then we can replace each three variables, key, plain text, and C, with one of the variables like hi minus 1 mi or hi minus 1 XOR mi. So of course we can replace them by a constant too. So this gives us 4 to the 3 possibilities, which is 64. So you can kind of convert a block cipher into a hash function in 64 different ways. But out of these 64 possibilities, 12 of them are considered as secure. And more importantly, these 3 of them are the generally considered as secure, and they are Davies-Meyer, Matthias-Meyer-Oseas, and Miyaguchi-Prenel constructions. So we will see how it works. So let's start with the Davies-Meyer construction. So this is a block cipher. It has two inputs. From here, it gets the plaintext block, and from here, it gets the key. So a block cipher uses these two information and produces ciphertext here. So just taking this picture, this block cipher, we convert it to a hash function like this. So instead of the key, you use the message that you are going to take the hash of it. And instead of the plain text block, you use the output value. So initially, since you don't have an output value, you can use an IV here. But after the first encryption, you will get the next compressed value and take it here. So increase i's and do it again and again and again. So it doesn't matter how much message information you have. After repeating this information, you will finally produce an hn value, depend if you have n message blocks. you will produce HN, which will be your hash output. And for instance, if this is AES, the block size is 128 bits, so your message digest will have 128 bits. So this is one way of constructing a hash function from a block cipher. So let's make a small trick on the picture. So this is the next picture. You can ask what has changed. We just switch the places of HI-1 and MI. If I go to the previous picture, this was like this. At WS-Mayer construction, you have the message block as the key and the hash value as the plaintext block. But in Matthias-Mayer OCS construction, you have the compressed value as the key and message block as the plaintext block. And idea is the same. You just switch these places of these two values. If you go to the third and the final construction, Miyaguchi-Prenel construction, now we have an extra arrow here. So this value also XORed to the final value. So these three constructions can be used. And as far as I know, most of the time, these are secure depending on if your block cipher is secure. But you can also construct an hash function yourself. So in these cases, we generally consider iterated constructions. So many hash functions adopt an iterative design to accommodate a variable length input. Markle-Damgard construction is the most famous one. Message M is divided into fixed length blocks. So you divide it into, in this case, T+1 message blocks, and you apply a suitable padding. Message blocks are compressed one after the other to produce HI using a compression function F. HI is called a chaining variable and used in the compression of next message block MI+1. In other words, compression function uses MI and HI-1 to produce HI. So this was the thing we just seen when we were considering block ciphers and turning them into hash functions. So H0 is fixed and specified as a part of the hash function specification. So we call most of the time IV, the initialization vector. Sometimes the finalization operation is applied to overcome some attacks. So here's a general picture how the Markle-Damgard construction works. So you have your message. You divide it into blocks. Block length depends on the compression function you are going to design. For instance, in, I think, SHA-1, this is 512 bits. So you divide it into blocks and apply a padding. Then, as an input to your compression function F, you take the first message block and IV. So this function compresses it and produces an output H1. So this H1 has a length, we call it a message digest, and its length depends on the hash function you are using. For instance, SHA-1 has 160 bits, and SHA-2 has many different versions from 224 to 512 bits. So if you have more than one block, now you take this output and put into the compression function again, take the second message block, continue in this way. So this is how Markle-Damgard construction works. So it all depends how you define this F function. So soon we will see examples of these constructions, and MD4, MD5, SHA-1, RIPE MD, and SHA-2 are examples of Markle-Damgard construction, which we'll be seeing in our next video. But in the recent years, cryptographers also suggested a different idea that is called sponge. So we can use the sponge construction to design a hash function. So in this case, you have a big internal state. So sponge functions have an internal state, which is, of course, depends on the algorithm that you are going to design, but most of the time it is larger than the block sizes of block ciphers. So you divide it into two parts, and one of them is R bits and the remaining is the C bits. This is called the capacity and this is called the rate. So this internal state, you start putting your message parts into this internal state and perform some operation on this internal state, some kind of a permutation, then keep putting the messages inside this big state. And finally, when your messages are all over, you start to produce outputs and perform the F function again and keep producing outputs. So it is like a sponge. You squeeze it and ZIs are produced as an output. So in this case, you absorb the message, then you squeeze the sponge and produce the outputs. So this is the idea. Because SHA-3 is an example to a sponge construction. So our final example in this lecture, in the topic of cryptographic hash functions, we will briefly mention how SHA-3 works, and it will have this idea because it is a sponge construction.